Hey everybody, Roger again. This time I'm going to talk to y'all a little bit about equilibrium. And so, equilibrium, what does it mean here? Equilibrium. So, in chemistry, equilibrium means that a chemical reaction can go forward and back, and does go forward and back. And that's indicated by these arrows, right? These reversible arrows. So that the process is thermodynamically and kinetically reversible. So we're just going to say reversible. And I'll fix this whole shake thing eventually. So, for example, we could have weak acid H, A meaning the anion, right? Making H plus A minus, right? And what we mean by reversible is that when in a thought experiment, if we just suddenly make a bunch of HA atom or molecules appear in a solution, that they will immediately begin statistically to distribute between H plus and A minus. So this will dissociate, and then that dissociation will reverse, right? And so there will be, if you put in, say, X moles of this into water, then originally there'll be, neglecting the autoprotolysis, there'll be 0 moles and 0 moles. And then there'll be X minus dissociation, and then dissociation amounts in there at equilibrium. And there'll be some approach, right? And H plus and A minus will be created in equal quantities, and HA will be depleted in the same quantity, right? So now another thing about equilibrium that's kind of cool here is that it's governed statistically by a simple formula. And the simple formula is that there's an equilibrium constant. We could say here Ka. This is an acid dissociation equilibrium constant. And that guy will equal the products over the reactants. So it's going to be equal to the H plus ion concentration times the A minus, the cation or the anion concentration over the undissociated ion concentration. So that means that this will be, in this above equation, this will be D times D over X minus D, right? So, so the beauty of this equation, right, is not that it's complicated or tricky or weird or anything like that, but that it determines the concentrations of these three species in solution. So whenever you have an aqueous solution, for example, a solution of water, you will have an H plus ion concentration. And if you have this acid, HA, in there, you'll have both this and this in a ratio that's determined by the H plus ion concentration, right? And if you know one, you know the other. And it's because of this equality here, right? That an equilibrium constant means that the H plus ion concentration times that divided by that is always equal to Ka. And I know that's kind of an obvious thing to say, but I guess I'm just attached to it for some reason. So maybe we'll come back to it. So it means an equilibrium constant means that these concentrations, the concentration product, equals a constant. right? And that applies to reversible reactions where you can define all these species, and that's not uncommon at all, right? So you could take, for example, the weak acid, that's acetic acid, that's CH3COOH, right? There's a simple carboxylic acid, right? And that's going to dissociate in water, right? If you put this into water, that will dissociate into CH3COO minus and H plus. Right? The alkylated form of H plus is H3O plus, but I'm just going to show it as H plus here. Okay, a little bit of shorthand for now, right? And the equilibrium constant, KEQ, is equal to Ka, right? A is for acid, right? It's just a special, just another name for an equilibrium constant. And that is equal to 1.75 times 10 to the minus 5. And that is equal to the H plus ion concentration times the acetate ion concentration divided by the undissociated acetic acid concentration, right? So one of the things here that I just like to emphasize real quickly is that you can dissolve acetic acid into water, right? Acetic acid without water is it's a little bit noxious, but it's a liquid, right? And you can add water and they will mix freely. And then once they mix, you'll get some undissociated acetic acid, some dissociated acetic acid, right? And water normally has, neutral water has 10 to the minus 7th molar H plus, and then that will increase by some amount if you added this pure acid, some amount X, right? And similarly, this is a good lesson as you're going forward. There's going to be bases, so there will be, for example, CH3, 3N. So what I've written here is trimethylamine. Right? This is trimethylamine. Right? And trimethylamine, if you add it to water, you can say plus H2O will make CH3, 3NH plus, right? Plus OH minus. Right? So what we have here is base. This is a weak base, right? And this is a weak acid, so this is a weak base. And they're weak because these equilibrium apply under normal conditions. So they don't completely dissociate in water, or they don't completely react with water to form base, right? That there's under normal conditions, normal concentrations, there's an equilibrium constant that you can write like that. So these are called weak acids and bases, right? And this has a KEQ which is equal to CH3 NH plus concentration times OH minus concentration divided by CH3 N concentration. Water is neglected because its concentration almost never changes, and that concentration is absorbed into KEQ as it is in all of these aqueous equilibrium constant expressions, right? Actually, let me try to move my webcam just a little bit back here, sorry. And so here's the weak acid, weak base expression. And you can also have an equilibrium constant that involves like a phase change, right? So a phase change here could be like the dissolution of a solid. You could have silver chloride, for example, solid, right? And this would look like a beaker sitting on your benchtop full of water with a pile of silver chloride in the bottom, right? Be solid in water, right? And this solid is only slightly soluble, and so when you dissolve it, it will form Ag plus ions and Cl minus ions, right? Those are a couple of possible likely products of the dissolution of AgCl, right? And then the KEQ for this is KEQ, and it's called KSP, right? Just another name for KEQ, and that is equal to 1.8 times 10 to the minus 8, right? So now let's do a quick calculation of an easy one here. Let's calculate the Ag plus ion concentration in water at equilibrium with silver chloride solid. Okay. In that case, this is a little bit easier because the AgCl KSP expression, right? If you use the formalism that we've been developing, right? That I said, well, that's going to be products over reactants. It'll be Ag plus times Cl minus over AgCl solid, right? But AgCl solid is what we refer to as a constant activity, right? So whenever you have solid in equilibrium with this dissolved form, it's defined as having unit concentration, which is another way of saying that its concentration is absorbed into the KSP here. So this is 1.8 times 10 to the minus 8, right? And so whatever sort of effective concentration this has, it's the same whether there's a lot or a little in solution, and its concentration is about 1.8 times its concentration is absorbed into this constant 1.8 times 10 to the minus 8, right? So if we have just water plus AgCl solid, then the only Ag plus and the only Cl minus that appear are from the dissolution of AgCl. And we can say that this is the constant part, right? So this is 1.8 times 10 to the minus 8 is equal to Ag plus times Cl minus, right? Just those two things. And since for every Ag plus that's produced, there's a Cl minus that's produced, right? We can say that this is equal to Ag plus concentration squared in this case, right? Okay, so 1.8 times 10 to the minus 8. And we just take a square root of that value. Hold on just a sec. And I'm going to say that 1.8 times 10 to the, oops, I don't know how to do that, exponential minus 8. There we go. Oops. Oh, shoot. Oh, forget it. Hold on. Okay. So that's going to be 1.8 times 10 to the minus 8. That's how you do it there. And then we're just going to take the square root of that. And that's going to be 1.34 times 10 to the minus 4. So hold on just a sec here. This guy will equal Ag plus equal the square root of 1.8 times 10 to the minus 8 equal about 1.4 times 10 to the minus 4. All right, and so this is a concentration in molar. It's going to be moles of silver ion per liter. It's actually fairly substantial. It's about a tenth of a millimolar. And so while silver chloride is quote unquote insoluble, it is slightly soluble. So it's called insoluble. So this is just an example of how to do an equilibrium calculation. We'll go over some of the slightly more complicated versions in the near future. Alrighty, guys. Thank you very much.